My name is Philippe De Brouwer. I live in Krakow. I am here a few things. To start maybe from the bottom, HSBC is the one that really pays me. And so HSBC in Krakow has a service center. We grew pretty fast. In the last 5 years, we grew from around 1,700 people to 5,000, below 5,000, 4,700 right now. And it is still developing really very fast. Krakow and Poland is becoming a major hub in the world of service. And okay, there is somebody who just joined who has the microphone open. So if you could go on mute, that would be great. And so what HSBC does in Poland is many different things. We are basically one of the service centers of the bank. So HSBC is a rather large bank. It's probably one of the most complex and one of the most spread out banks in the world. There are bigger banks or banks that have a bigger balance sheet, but these banks are quite simple and they have a very, very simple business model. They lend money to people in China and they get funded by the state of China. And so there are 3 banks or something like that that are bigger. And then you have HSBC, and then you have Citibank, and then there is a long while nothing. And then you have smaller banks, more local banks. And if you then compare Citi and HSBC, well, Citi is more the retail bank, so for people like you and me, and HSBC is rather the bank for the large corporates, so for our employers, the likes of Shell, British Petroleum, BMW, Mercedes, Google, those type of companies, they all bank with HSBC. And so Poland is becoming a very important service center. In Krakow at this point, we have 120,000 people in service centers. It is really small, but it is a very interesting wave of offshoring. You see, the first wave of offshoring was very simple processes, massive employment, and many things are in India. Now, many things are in Krakow, but it's another type of offshoring. It is more the offshoring that is for the very specialized processes, which are very difficult to describe exactly, and which require that people have an opinion, that people stand their ground, that people think and change things. And so that is the thing that I try to support in Krakow. More in particular, I do risk management for the bank. And so I'm trying to attract all type of interesting jobs around risk management, like specialists in, probably the biggest team that I have is specialists in mathematics. And so I have a team of about 100 people that are half of them PhDs in mathematics, and they will check all the mathematical engines of the bank. All the financial models that we have to trade on the stock exchange, to lend in Russia, to do cash flow matching in the United States, everything will be checked. And that is a worldwide team, but half of that team is in Krakow, so most of the things pass through Krakow. Okay, for the rest, I also teach from time to time, and probably most of my time I spent at AGH, one of the local ones. And I also am honorary consul for Belgium in Krakow. Honorary consul is basically some kind of thing that you do in your free time. You don't get paid for it, but if somebody has problems, that person can call the local consulate, and then you can help people that have troubles. Typically in Krakow, that is people lost their passport, and I just have to go here, and basically what I do is make them a temporary passport. And so I have some small stock of empty passports in my office, of course, very well under lock. And okay, so here I am about innovation. And when we think about innovation, probably there are some great innovations around. And probably the greatest are the oldest ones, isn't it? Maybe it is seeing that grains grow when you put them in the ground and starting to do farming. That's about 10,000 years ago. Maybe it is the wheel. The wheel is like 3,000 years ago. The use of bronze is very similarly around 3,500 years ago. Or maybe it is iron, which is 1,700 years ago, if I'm not mistaken. You see, those things come at a slow pace. We invent farming and then 7,000 years, nothing major happens till we start with the wheel and bronze. And then another 2,000 years, not much happens. But it is only once we had capitalism that somehow we seem to go faster and faster with many different things. And the first thing that comes to mind is obviously the steam engine. The steam engine is something that totally revolutionized the world and changed how we work, but also how we live. You see, before the steam engine and the potato, in all fairness, we were living largely in countrysides. We couldn't sustain big cities, and there was no reason why we would have big cities. Cities were reasonably small. They were trading hubs of small sort of labor, of artisan labor. But it is only with the steam engine that we created a capacity of producing things massively, on a massive scale. And so the type of thing that you have is basically this kind of enormous piston in which you have a boiler to boil water, and that piston will push this thing here forward. That thing will turn around, and here you have an axis that propels some sort of machine. These machines were heavy, so we built one of those steam engines, and then you had that axis coming out, and then on those axes you had in each and different room. It went through the different rooms, and you would have different appliances on that axis.
Sorry, Filip, I would just... Sławek, wycisz, bo jesteś na telefonie połączony.
Sorry, wyciszyłem, sorry. Okay, sorry.
Okay, Filip, sorry, but it was very noisy.
Thanks for helping out. I think that's indeed useful. So you're all very welcome to interrupt and ask questions, share stories, or even challenge what I'm doing here. But indeed, if you're not speaking, it's best to go on mute. The thing is, however, that steam engine wasn't really new at the moment James Watt invented his machine. He could basically base on the Newcomen engine, which existed already and worked. Now, the Newcomen engine wasn't a very practical one. The Newcomen engine was a one-stroke engine, and so it only gave power with a piston going in one direction. So it wasn't strong enough to do anything useful. And Newcomen could already base his inventions on work from the Arabic world and even the city-states in Italy centuries ago. So what is interesting is that steam engine, at the moment that it takes off and revolutionizes the world in the end of the 1700s, it wasn't new, but it was innovation. And here you see the big difference between scientific development and innovation. Scientific development is probably, well, already early on, we know how to use steam, and we know what steam can somehow do, and we already theoretically have some concept about a steam engine, but it is only in the end of the 1700s that James Watt built us a machine that is strong enough. And then we have the theory, the engineering, the raw materials available, and honestly, we also had the potato, because the potato was the thing that would help us to feed all the people that we brought to the city. And the rest is history, isn't it? Once we had a steam engine in England, it spilled through to Belgium, France, on the continent, and we built many sort of appliances with it. The first thing were machines to weave cloth, but we could basically do everything with it. It really revolutionized everything. And then you see that every year we have something like 10% more. And so then you see that growth from, let's say, 100, 110, and so on. And that is an exponential growth. Every year, a certain percentage more gives you an exponential growth. And we're just through the pandemic of COVID. So we kind of understand what an exponential can do, isn't it? One person eats an undercooked bat, infects 2 people, and those 2 people each in turn infect another 2 people. Then you have 4, and then you have 8, and then you have 16 and 32. And today we have 3.5 million people dead. One person, one bat. See, that is what an exponential does. An exponential explodes because in our universe, on our planet, nothing is infinite. So the exponential has to stop somewhere. And so also with capitalism. Capitalism is really great in growing 5%, 10% every year. But at some point, you hit a wall. You have market crashes. 1857, 1866, and 1873. And after that one, we have what is known as the Long Depression. And it seems like all that we have built there was gone. The depression was so deep and the misery was so overwhelming that it gave rise to a new way of thinking and an alternative for capitalism, which in Poland, unfortunately, we know what it is about, so I won't elaborate on that one too much. But anyhow, after the rise and the fall of the steam engine, we were ready for something new. We were ready for the steam train. Obviously, the concept of steam train wasn't very new, because already in the early 1800s, 30 years after James Watt built his steam engine, we had the first train. But you see, before a train can be practically relevant, before it can be applied, before it can sustain economic growth, you need some scale. You need more than just one railroad. And so you have to build the railroads first, you have to build the trains, you have to make the trains more efficient, and it's only then that you really add something to the economy. You see, what has been added at this point is actually quite interesting. Because of the steam engine, we had mass production. And then, because of the train, we had mass transport. And you understand the logic, why that could again transform the economy, sustain exponential growth. Excuse me? Okay, I think somebody is still not on mute.
Philippe, but I think you can mute everybody. As a host, I think you have this feature.
Right.
Well, I'm not sure, but I think
Disabled.
Maybe I'm wrong.
Annotation, had video panels, video settings. I'm afraid I don't have it or don't see how to do it.
Maybe when you click on participants, you can mute everyone, or at least when you go to the participant that has just lately joined, you can mute the person.
Correct. I'll just do that. Thank you very much, sir. And let's continue. Okay, so the steam train gives us mass transport after the steam engine has given us mass production. And while it is not based on anything new, it's basically old technology that was ready, it was able to propel another phase of exponential growth. Unfortunately, also that phase of exponential growth had to stop at some point. It couldn't go on forever. It ended in the panic of 1901, and to some extent, ultimately World War I. And it's only after that that we could restart with another phase. And that was based on the internal combustion engine. So that is basically a diesel or a gas motor, so benzina motor. These motors are much lighter, so you can have smaller machines, and obviously that is the car and the truck, or motorcycle, of course. And that gives us now individual transport. That gives us an all new world of delivering goods and transporting people. And again, we see why it is relevant, and we see how it can really sustain a wave of economic growth. Another thing that happened more or less at the same period is that we understood better how to use electricity and magnetism. And that understanding allowed us to produce a lot of small appliances. Some you already have seen here on that car. We have light bulbs. Most early cars, of course, didn't have too much electronics inside. Now you will be far-fetched to find anything that is not electronic in cars. But anyhow, that was a period that we started to build appliances to help us to do daily jobs. Iron clothes, wash clothes, and tools that turn or push or something like that. Massive explosion of small tools based on electricity and magnetism. Massive explosion based on cars. And we already see the pattern, isn't it? First of all, it wasn't anything new. Light bulbs, for example, already existed, or the concept already existed, and we just had to refine it till it was good enough to be commercially available. We had electrical motors for cars already. First, gasoline motors were already around for decades. But you see, it is only just before the war, and then, of course, after the war, that we could start mass producing cars, building factories that would produce those things with great efficiency. And here we kind of understand another aspect. It is not only something that can sustain economy or put structural things in place for the economy, it is also something that has to come down in price. You see, unlike the steam engine or steam train, regardless the price, those things probably didn't decrease too much in price. Cars, they have another trick. Because of that mass production, they can become cheaper. And because they become cheaper, the adoption rate will increase. And again, that is something that will work exponentially. If you can reduce the price of your car every year by 2%, generally speaking, you can expect that 1 or 5% more people can buy your car the next year. And if you say every year a few percent more, then you say exponential growth. And when you say exponential growth, you say, well, you're going to hit a wall. Nothing is infinite on this world. You're going to hit a wall with exponential growth. And so we have the Wall Street crash of 1929. That was the start of the Great Depression, ultimately World War II. And it was only after that that we were ready for yet another phase. That phase was based on the chemical sector. And that chemical sector, probably the things that speak most to our imagination is the plastics, like the PET plastic. Everybody has these Coca-Cola bottles these days. Very strong plastic, very light. You see, those things were based on a lot of earlier research. So this slide is quite active. And another thing that you might remember is the polyvinyl chloride, PVC plastics or polystyrene plastics. Those things, you see, they were around quite early. Again, we see that the technology that is based on not new things is able to propel the economy forward. In this particular case, well, it is the exponential growth for the economy, yes. It is things becoming cheaper, yes. But it is also a wave of innovation that here is very, very visible. Let's say with steam engines, steam trains and cars, that innovation was also there. It is just a little bit harder to put it in a slide. But did you know that trains, for example, steam trains, how fast would the fastest steam train go by the 1920s? Anybody wants to take a bet on that?
120.
160.
Absolutely. Great shouts out there. 120, 160. That was about the speed of a train in the 1920s. Honestly, the average speed of trains has come down over the years just because there is more and there is congestion, there are waiting times and stuff like that. But honestly, an electric train doesn't necessarily go a lot faster than a steam train. Steam trains could go really very fast. It is just electrical trains were more efficient to operate. Diesel trains were more, let's say, also more efficient to operate, and you don't have to continue to put in the coal, for example, so you can save on 2 people. Steam engines are remarkably efficient. For example, if you go to Ramsgate, a small harbor on the English coast, they have a steamboat that is put ashore years ago, and it's a kind of museum, you can visit it. And that thing is probably 100 years old, but its engine still works. And they basically start it every year. It's out of the water, but for a steam engine, that doesn't matter too much. So good old technologies. And also here, with our petrochemical industry, at some point it all comes down. And we remember the stock crashes of 73, 74, and after that we are again in economically very difficult situation. The next thing that takes over is obviously the electronic computer, isn't it? And that thing, as we all know, wasn't new at that point, but it was that point that the technology was ready. In the 1970s, the electronic computer was ready to be useful. If you wanted a hard disk, well, you still had to break open your building and have a crane to put in the thing inside your building, but it became useful. We still were using punch cards. Most computers didn't have screens, but it became more efficient than the alternative. And the alternative was basically storing information on paper or making a lot of calculations. For example, the first time when we have put people on the moon, 1969, we had electronic computers. Those computers, all together, the NASA had much weaker computing power than what you have in your pocket right now. This small phone here, it has not thousands, but billions of transistors. It has something like 3 billion transistors in its processor. A transistor is a simple gate, yes, no. A lot more than the whole NASA combined when they have put first people on the moon. And so they had to add to their electronic computing power people's computing power. So there were teams of people, typically ladies, because they were very precise. And those ladies were just with pen and paper, making all the calculations, where the machine was, what they should do, how to correct the course, and all those things that were crucially important for the moon landing. But you see the 70s, the 80s, computers get used more and more. Because they get used more and more, there is more money for development, for R&D. Because of that R&D, the things get better, but also the things get cheaper. and the rest is history. But that better here is very interesting. Unlike, sorry, the slide is a little small, but what you have here is just a normal linear scale of time. And it starts in the 1970s, and it ends here more or less where we are now. In all fairness, you can draw that line through to the 1870s. And the computers that we had then would basically fit that line more or less here. The first computers, they were very simple calculators, logical gates, basically simulating transistors in some way. And the first conceptions were made based on steam engines, not on electricity, based on steam engines. Since then, the number of transistors has been evolving according to that line here. And what you have on the y-axis, that is an exponential scale. So here it is 50 billion, here it is 5 million, sorry, here is a 5 million, there is a 5 billion, 50 billion. And so you see it on a similar scale, it doubles every time. And so that is commonly known as Moore's law. Moore's law tells us that the number of transistors in the processing unit of a computer somehow doubles every 2 years. That is a very fast exponential growth. There were much more Moore's law types with computers connected. For example, the speed of the processor was an important one. And what is happening with that one at this point? It basically stopped growing, isn't it? The speed of a processor was in the early 2000s, I think around 2005, then came up to 3.45 gigahertz. It still is at 3.45 gigahertz. There is another Moore's law in how small the transistor is. So the basic element of a processor is a transistor. It's a gate that can be open or closed, 0 or 1. And that basic gate, well, first we had the steam engine concept, and then we understood electricity a little more. And when you see one of the first computers that was important and reliable that we could use was the ENIAC. The ENIAC was using this kind of glass tubes, cathode tubes, that somehow functions like a lamp, but where you had silver plated on the inside, and things would work that electricity could go through in one direction, but not in the others. Programming the computer was basically adjusting those tubes. So it was a very physical thing. And then, of course, the big thing happened when we invented a new type of transistor. Okay, that strange word, metal oxide semiconductor. It basically means we were able to take these tubes or whatever the transistor was and bring it down to materials, to metal, silicon. And because it was brought down to materials, so you just had to have sand and copper and things like that together, you could obviously invent ways to make it smaller and smaller and smaller and smaller. And that, of course, also happened. That was another Moore's law that is happening. And of course, when you start from things that have the size of a milk bottle, then you can halve it. You can halve it again, halve it again, halve it again, halve it again, and it will still be reasonable. But at some point, you are in the 2020s, and then halving things are at a scale that becomes atomic. And of course, you hit another wall, because you can't really split things that are, well, you can split atoms somehow, but that won't, I said, you're in a different world, you're in the quantum world. We'll talk about that later, but you have hit somehow another wall. So in summary, in the computer, we have seen a lot of interesting Moore's law phenomena, like doublings or halvings every certain time, like the speed of the processor, the number of transistors, and that number of transistors, honestly, is still going on. We build supercomputers, and those supercomputers are getting better ever and ever, for now at least. The speed of the computers has hit a wall. The miniaturization is still going on, but that seems to slow down because of the technical, say, the engineering challenges that are around. Anyhow, that computer, while not new, you see, in the 30s, we already had that concept of the computer based on the steam engine. Okay, we had electricity, but Charles Babbage was kind of a conservative person and said, well, I don't trust those new stuff, electricity. Well, not for me. I will design my thing around a steam engine. And then we have the famous Ada Lovelace, who was the first programmer in some way because she started to write code for the machine that hopefully would soon exist. Honestly, it did not come to fruition. And so the computers that we had in the 1800s, they were not really finished. Although the plans were there and part of the machines have been found back recently, and in the UK, I believe Imperial College is building now, trying to finish that steam engine thing that 100 years ago we started. Another interesting thing is that it allowed us to build up some kind of network of networks, which now these days we know as the World Wide Web. Okay, what this line means, www, is developed in CERN. Okay, that is not the internet, of course. Internet is from here. That is a technical connection. But this www thing is the HTTP service, so the website type of communication. Before that, we were using other things like Telnet, FTP, and so on. And of course, emails were already around. IRC, Internet Relay Chat, where you just type a message and somebody answers the message. That was from the 60s. That is not from the 90s even. We start to call things different, by the way, but anyhow, it is not hard to see how computers sustain exponential growth. And when you say exponential growth, you say you're going to hit a wall. And indeed, we had the dot-com bubble of the 2000s, and a second real deep drop of global meltdown, which was somehow fueled by strange things we were doing in banking, but on the other hand, had a lot to do with another wave of technology coming up to its end. Right, so here we are. What about the future? What is going to be next? Maybe let's take a second break here and start a new whiteboard. And okay, I think we can clear all drawings. Okay, and if we now just pop some text on the whiteboard and give some keywords of what you think will be important for the future. There are no wrong answers because I don't have a crystal ball. Of course, I have an opinion, and that's what we will be talking about later. But what do you think is ready to fuel a new wave of development?
I think you have to enable the whiteboard to be active. At least I cannot draw anything. But
oh, right.
Or maybe that's just me. But
okay, I wouldn't know how. I don't see any option.
No, because previously I had this icon of this pencil in the, and I could just write something on the board, but now it seems like.
Okay, let me stop share. Let me retry. And if the whiteboard still doesn't work, Oh, it
Okay,
seems to
now
work.
it's working. Yeah, yeah,
Good.
now it's working. Yeah.
Okay, so let's just pop up some things that you think make sense. Quantum, AI, ML. Data. Big data, small correction, indeed. Okay, and for the rest, we don't seem to have too much inspiration. IoT, yeah, blockchain technology. But by the way, if you prefer just to speak, just unmute yourself and that's also fine. Nanotechnology. Okay, I think we have some great things, new materials, fascinating one, indeed. Okay, I think food, absolutely. I can't really read what food technology, could it be that one? But definitely, yes, around food, you can expect quite interesting things. Okay, let's just wait for Margosa to add something and then. Right. Okay, Margosa, I'm afraid you will have to read it out for me.
I think it's industry.
Industry, okay, that would make a lot of sense, yes. So there are indeed, not surprising probably because of the audience that we have on the line, a few very, very good suggestions on the board. We don't have too many things though. People seem to converge around, probably what we have is things around computers somehow in one way or another. And then of course, computers kind of intersects with nanotechnology. We have new materials which are a little bit by themselves, and we have food. And within the computers, quantum probably plays a specific role because it could be connected to computers, but not necessarily is. Artificial intelligence and machine learning, big data, Internet of Things, blockchain technology. Oh, and biotech is indeed here. That's probably the odd one out in that group and probably deserves its own category and probably very much connected to what we have in the food industry. Okay. So let me go back to my presentation here. And that is indeed largely the things that I was thinking of. But before we get there, let me take a step back. You see, we have been talking about the steam engine, the steam train, the electrical and engineering revolution, the automobile, the petrochemicals, the computer, and so on. And it was always the same thing. There was some technology that was maybe not new, but definitely mature technology that could fuel exponential economic growth, that would create a new wave of welfare, wealth, convenience, but at some point hit a wall because of the exponential growth and a deep economic crisis. Those cycles seem to come in periods of something like 80 years somehow. So it goes pretty slow. And actually, the person who already to discover that was Kondratiev in, I believe, 1936 or 1935. So kind of early on, more or less here, that person discovered we have these economic cycles and they seem to work like a clock. Of course, that could only start working more or less here, where we had somehow the whole world together in a way that we could conveniently go there and exchange goods and information. So the new world was discovered, and we had societies that were functioning on the base of capitalistic thinking, so the logic of free enterprise. And so that free enterprise seems to be very good in taking a new technology and then having many people developing innovations or just doing more of the same stuff and riding that wave upwards. Unfortunately, capitalism doesn't seem to have a mechanism in place to avoid the ride downwards and the deep economic crisis that followed on the base of that. Part of that, I believe, is the way we think about risk, but that's another story. So remarkably, that person writes a theory in 1936. And after that, we have the petrochemicals. Okay, automobiles on this plot. I have put the automobiles basic, oh, sorry, I shouldn't hit the mouse here. Okay, how do I go back? Oh, here we are. Good. So automobiles, I had put them in this cycle. Automobiles have been being part basically of two cycles, in all fairness. But okay, apart from that, the most important thing here is not where you put automobiles. Of course, the most important thing is that that cycle seems to repeat over and over again. And this is an image that I took from the internet, you see, quite early on in the 1990s. I'm quite sure that those people have been able to continue their plot with the global meltdown, and we're probably somewhere here in the 1920s. So here we are. This is a point from which we will see economic growth. That is, I think, an amazing thought. That is a fantastic, great message. But indeed, the question is, what will bring that economic growth? Another aspect is, of course, that these type of cycles, they only seem to be possible once we had nailed the scientific method. And capitalism and the potato. Of course, a potato is kind of euphemism because it was the thing that we had available here and we could start our cities around those steam engines. But we were able to feed people, bring them together in cities. And we also had a scientific method in place. And a scientific method is actually a very simple model where you start from a certain question, test your question, collect your data. Once you have your data, do stuff with it, check, make predictions, and see if it works. And then make conclusions. And if you're wrong, you start all over again. And on the way, you publish your work and you allow other people to check and draw their own conclusions. That is quite essential on the scientific method. See, before that, we had many different ways of thinking. We had the great Greek school, for example, where we conjectured things like, what if I imagine that geometry is on a flat plane and I can just one point and I can have another point, and through one point is just one line, and then I can have a third point and just one parallel line with the previous line. That works. But they also conjectured, for example, well, insects are animals without blood. And they never bothered to check if those animals really have no blood, or the blood is just a different color and you just don't bloody see it. It is only when we had a scientific method in place that we were able to go very, very fast. And that helps us through those cycles. So we have, first of all, we have to be able to sustain cities. So we need a food source. The second is we need a certain form of globalization, because that economic growth is expensive to finance in the first place. And the third thing is you need definitely the scientific method. When all those things are in place, and as you have put on the whiteboard yourself, we have very strong candidates to sustain the next wave of growth. So I will now very quickly walk through them and basically argue that the first wave of machine learning and big data, so the things around computers, that these things are rather ready. One that wasn't on our whiteboard is robotic process automation. Many people like to short RPA. Nanotechnology was on the board. Biotech was with different words. We were referring to food and things like that. And quantum was on the board, not so much as quantum computing itself, but it all seems to indeed go a little bit faster. Okay, while there is a lot of value in trying to find out which is the technology is the most important, I think the key thing is there will be something, but if we look good and carefully, we might even forecast what is going to come in future cycles, 60 years from now. Okay, so first of all, artificial intelligence, we will have a very short presentation basically to demystify how certain things work. For example, we have driving cars, and driving cars, we all know that that became possible because of what we call deep learning. And while it is shrouded in mystery, it is actually a very simple way of thinking where we try to capture the essence of the human brain in some way, put that in a computer, and then see what the computer does with it. And so the machine can in some way learn. We give it a picture of how a person looks like or how a person behaves, and we let the computer figure out itself that it shouldn't crash with people and should avoid people by doing certain actions. Instead of trying to program concepts like a person is something that has a head, has arms, has legs, and things like that. That, I think, doesn't need arguing. Artificial intelligence and machine learning, robotic process automation is here. That is working. And going back to my very first point about the service centers that are exploding in Poland, that is largely because of that technological wave. All big companies, they are investing in technology, they are investing in streamlining their processes or basically allowing machines to do processes that people are doing today. For example, in banking, we have a lot of rules to comply with. And okay, every company has internal regulations. But in a bank like HSBC, that becomes impossible to read all those regulations. And then, of course, you're in a very dangerous space. As a human, you don't know what to do. If I would read all the laws that are important for banking, all the internal regulations that we have, all the papers that the regulators write to say what we have to do, how we have to do it, there is literally hundreds of thousands of pages of things to go through and to remember. So people can't do that. So you will have specialists. We have armies of specialists in different domains. And then you can ask those specialists to discuss about what to do. But again, here machines will help out. And we're very close to machines telling us, okay, this is in line with the law, go ahead. Or you shouldn't because there is that law and there is that regulation, and that's why you shouldn't. So things like lawyers. Also, and I believe it's also in Imperial College, last week there was a breakthrough in allowing computers to understand normal language and program on the back of that. You tell the machine, I want to connect to this database, pull out these customer IDs and these products and build me a screen that looks like so and so, and the computer will build the software for you. So you see, it's almost limitless, isn't it? And that is, and again, another exponential growth. But here is another interesting one. Here is also a potential exponential growth of intelligence. Well, we shouldn't be afraid that a steam engine would become intelligent. But here we're trying to build machines that somehow mimic human intelligence. And those machines, they get better every year. Our brain, well, has been going through some improvements, probably up to last something like 5,000 years ago. But even if you take a person 10,000 years ago at birth and you would put it in our society, that person would probably have issues in that society to follow somehow. We need some more genetical mutations. But take a person of 1,000 years back, 2,000 years back. That person would probably not stand out against the crowd of people that we have today. That person's brain is more or less the same as your brain. However, take a machine of 20 years ago and take a machine that you have today, it's a world of difference. So imagine that you can build a machine that is able to build another machine that is actually slightly more intelligent than machine one. And so machine one can build, let's say in whatever time, 5 years time, a machine that is 5% more intelligent than machine one. And so that machine number two can build another machine, machine number three, that is 5% more intelligent in a time that is 5% faster. And you see where I'm going, isn't it? The next one can do it in a slightly shorter, 5% shorter. And that will converge to a moment where intelligence will just explode of those machines. That is not new. The singularity was first described in a paper in 1965. And till now, we have no theoretical arguments to say why that should not be the case, or we can't see what hurdle we're going to have before that singularity arrives. Okay, just interesting aspects. So information intelligence seems to be part of another potential exponential growth. And actually, we're kind of in that exponential growth at this point. But for now, artificial intelligence helps us to do all kinds of things. For example, did you know that wearing a ski mask is not a perfect protection anymore if you don't want to be recognized? With artificial intelligence, we can take pictures of police that behaves particularly brutal and find their Facebook profile. This is obviously technology that was used by our eastern neighbors in Belarus. Then there is nanotechnology. You probably heard about Vanta Black. So here we have two sculptures, two bronzes, and both of them are the same person. Both of them are exactly the same. Now this one looks like it is just with Photoshop cut out and the image just made totally black. Well, it is not. It is simply painted in Vanta Black. And Vanta Black has basically small graphene tubes, but those tubes are on a molecular level. And so light falling on that graphene will get stuck in that tube and not get out. And that is why this thing doesn't reflect light. That is one application of nanotechnology. But honestly, you'll be far-fetched to find another one. So graphene is basically a layer of carbon hexagons next to each other. So graphene is a material that we can build, manipulate, and use, but it is really at atomic level. It is just one layer of atoms thin. That's really remarkable. It seems to be reasonably strong for its width, and so there are probably plenty of applications that we still have to think of. So here is that carbon nanotube, and here is our graphene. Those things, they are around, but probably not yet ready. You see, the real application of nanotechnology is things like that. Build a robot that is small enough to go in your body and isolate viruses or bacteria and say, okay, well, this one is not very good, so here I will inject some material that makes it explode and deactivates the thing. So we are pretty far in building very small robots, but we are far from building robots that are intelligent enough on that scale, cheap enough to be usable. So that nanotechnology probably not yet. Another thing that was mentioned is biotech. Now, if you want a mature technology, that's probably the one, because that is the one that we started like 7,000 years ago. We started farming. And from the day we started farming, we were in the business of genetically modifying plants and animals. And honestly, we started a lot earlier than that. 15,000 years ago is more or less the period where we started to work together with dogs. Dogs joined us 15,000 years ago. And of course, if you would have a dog that bites, you would hit it on the head and the thing would be dead and it would not have offspring. If you would have a gentle dog, you would make sure that it thrives and that gentle dog would have the offspring that it desires or deserves. So we kind of gave the dogs a stable food. We gave them a way to connect to us emotionally, and we basically took their choice of partner away, and by that started genetically modifying them. Okay, plants, they don't have agency, so it's kind of easier. You just have grains, and you take the best grain, and you put that in the ground next year, and if you do that for a few thousand years, you get a slightly better one. And if you continue, okay. All right, sorry, let me go back this way. Okay, here we are on our biotech. And so if you simply continue that way of working, you will improve your food source over thousands and thousands of years to something really very tasteful, really very nutritious, really very resistant to diseases or droughts or whatever you have in your particular place. So biotech is not new. Biotech will give us a lot of things. We have quite some tools already, and honestly, it will really make our world a better place to live. We will need less chemicals that pollute. We will have more stable, more nutritious crops. And if we still decide to use animals, well, we can have the ones that are less sick and suffer less and things like that. In the end, we should get better health for all of us. So biotech has a lot of promise. But my take on it is that biotech still has some way to go before being super commercially available. So here I have a slide with some animals. So discard this Homo sapiens here, and okay, there is one plant and it shares the same characteristic. So what do all those animals have in common? Does anyone want to take a guess what all those animals have in common? Okay, no guesses. Well, sorry, unless my speaker is on. So probably some of those animals you know, isn't it? Well, obviously, this one here is a crocodile. This one is a turtle. Turtles are probably the one to start with because you know they can get pretty old, isn't it? I believe there was one turtle that was like 180 years old, and it saved this species because it had fathered another 100 offspring. Saying that, that's kind of remarkable. So that animal here was like almost 200 years old, and it fathered a few hundred kids all at once. You see, when humans get old, they don't father hundreds of kids anymore when they are hundreds of years old. Humans, when they get old, well, they get some gray hair, they get more wrinkles, our muscles get weaker, and sexual reproduction kind of basically slows down or stops. At least at a certain age. Don't worry about it. You're all very far from that. But those animals, not. And all the other animals that you have on the screen here, they are pretty much the same. They don't really get old in a very similar way as we do. So basically what happens when we are getting old, our chromosomes, they split and the endings, they kind of get shorter. We have some redundant DNA at the endings, but every time a cell splits, that redundant thing gets shorter. And then at some point we start to cut in the relevant code. And then of course we get weak and older and all these kind of things. Those animals not. Of course, some are, let's say, weird and far away from us. Obviously the Hydra is weird. The Hydra basically stopped sexual reproduction 65 million years ago, more or less the period that the dinosaurs disappeared. The Hydra decided, okay, I'm through with it. I don't have sexual reproduction anymore. I will just do it by myself. And so that is the only one that is actually biologically immortal. That thing is 65 million years old. And so basically how it reproduces, it gets bigger and grows tentacles, and then it will break off that tentacle, and at some point that tentacle becomes an animal in its own right. And so it's the same living organism going on for 65 million years. 2 months ago, this guy was in the news. Anybody knows who it is? It's a Greenland shark. And the Greenland shark was caught in a fishnet, and it appeared the animal was 400 years old. 400 years old. That thing was swimming in the oceans just after we discovered America. Long before we had our steam engine, steam train, electricity, computer. That thing, that very same animal was swimming in the ocean. And then, of course, we have clams. Some of those clams, they can get hundreds of years old. Sea anemones, they can get up to 80, 100 years old, which for such small animals is really remarkable. Lobsters, very much the same. They grow up to 50, 60 years. And again, for animals of that size, very remarkable. And what they have in common is that just as the crocodile, sorry, not the tardigrade, okay, let me correct that. The crocodile and the lobster, they do not stop growing. They continue to grow. And that is part of the reason why crocodiles ultimately die, because they get too big to find food. One famous crocodile in Congo was Gustav. Gustav was a male crocodile, and he was about 17 meters long. So his mouth was about 2 meters long. So his main food source was becoming humans somehow. Humans would be eaten by the crocodile from time to time. People tried to hunt it. It had wounds of machine gun in its tail, survived the machine gun attack. At some point, it just disappeared because it couldn't find food that was big enough. And by the way, Gustav had a part of the river that was like 7 miles, so 10 kilometers up and downstream, where no other male crocodile would dare to come. It would just kill them. It would, however, allow female crocodiles, and it would take good care of the female crocodiles in that sense that there would be a lot of offspring. So you see, those animals reproduce more, or like these lobsters, they get sexually more active when they get older. Okay, then we have, of course, the tardigrade, which is a little bit an odd one. So it's an odd one because it's very small. It's like 1/10 of a millimeter, but it's hardly, you can hardly kill it. You can dry it completely, it survives. You can put it in outer space, it survives. You can, also the genetic material is remarkably resilient to radioactivity. So again, something we can learn. And obviously that tree is a tree in Sweden. It is 9,500 years old. So that tree was around when we started farming, that very same tree. So in nature, there are plants and animals that can live very long. And the promise of biology or biotech is, of course, to copy that and make sure that we understand why those animals live so long and so copy it for us. Now you can say, well, they're all quite remote from us. Definitely plants and sharks and stuff like that. There is nothing close to human. However, there is one guy that I wasn't talking about yet. And that is obviously this animal. It won't win a beauty contest, but it is the only mammal known that has a very, very low senescence. So it ages very, very slow or almost not. And just as the crocodile and the lobster, they don't lose their appetite for reproduction as they get older. This little guy here can get up to 80 years old, no problem, and being very productive in producing offspring on its way. So the holy grail or the ultimate promise of biotech is probably still in front of us. Quantum computing, okay, we will be spending more time on that in a minute, so I will go very fast over this one. But in short, we have certain algorithms that can do certain interesting stuff, like we can do optimizations. We can factor numbers, and factoring numbers is good to break all the security that we have now digitally, so encryption. And in its wake, of course, all the blockchain technology. We're very close to, let's say, some things we already have. Optimizations, they're here, but factoring numbers, we need much more complex quantum computers to make it really useful. We can do it, but for small numbers. And something really weird, like inverting functions without really knowing the function in the first place, which obviously allows us to search in unstructured data. So if you have data that is alphabetically, that is structured, that's pretty fast to find what you're looking for. But if data is not structured, like looking in movies, that takes a lot more time. Here, quantum computers can help. Again, we need more complex machines. And then they can also do something which we call solve large linear systems. Okay, what that actually means is maybe technical, but what it will give to us is deep learning. Deep learning machines at this point are limited to our computing capacity to fit them. And the computing that is needed to fit them is basically solve these large linear systems. So when we can have quantum computers that work better, you see we can do a lot of things. Well, we will have to find another way of encrypting stuff. We can search in data very fast, and we can have more intelligent machines. So things like driving, for example, that will be quite easy to get to. At this point, the only practical useful thing is this optimization. Remember Goldman Sachs last week in the news that they had done some optimization with a quantum computer. It sparked some more interest again. Okay, in conclusion, but before we jump to conclusions, maybe quickly dwell on the question, are we actually better off with innovations? Because you see, innovating stuff or inventing stuff, it's quite a different concept, but to have innovations, you need inventions. And inventions are quite awkward because once you invent something, you can't uninvent it. Uninventing isn't even a word. For example, once you have invented the atomic bomb, you can't uninvent it. The fact that we can build such bombs is part of human knowledge forever. So the problem with innovation and inventions is that it's like grabbing a colored ball out of a bag where you can't see what color the ball is unless you have it out. And it's only at the moment that you have it out that you can see what ball it is. We had a lot of white balls in that sense that they were positive for us. We had a lot of inventions that helped us to have better food source, more stable food sources, more safe environment and things like that. But we also had very dark balls like the atomic bomb. It's not a good thing to have around. The thing is that we never know that at some point you pick something out and it just destroys everything. That's not really impossible to avoid. And with the globalization and innovation and all this development that we had, there is a lot of misery, or at least the misery is very much visible. So the question is innovation actually good or not? Does anybody have a strong opinion about that one? Okay. Right. I don't think there is a strong opinion. So let me try to answer the question in a very simplistic way. If you just look at life expectancy from the moment that we have the steam engine, with some delay, it really seems to take off. Over the different continents, you see that life expectancy is definitely growing. You see, in a world that is unsafe, unhealthy, people die earlier. So even while we have now a lot of pollution, and pollution is not good, all right, but we're a lot better off than in the 1800s, where the life expectancy was only 30 years old. Another way of looking at that is to see how the wealth of a nation correlates to how long people live. You see that poor nations, people can expect to be 50 years old. In richer nations, it's rather around 80 years old. So that wealth, that growth, that innovation, those inventions, on a large scale, they make sense. But it is up to us, and definitely people like you and me, and people that are doing an MBA, they will have an important say in that. So in summary, the scientific method works, and data science is most probably the next big wave, or at least the start of the wave. And maybe we have things like biotech joining in 10 years, and maybe if we play it smart, we can go from one wave to the other without a major crash in between. And just for your information, that's not too important right now, So the book that I just had shown you, that book, what we have done now is largely talked through the introduction. Then we will spend some time on learning machines and showing how simple certain things can be done. And that is the part 5 of the book. And then we will have some presentation on quantum computing, which is not really part of this book. But if you want a reference for the first part of this lecture, then of course, since I wrote it myself, I obviously biased, but I would say I recommend that thing. Okay, so let me pause here. And before we move on, are there any questions? Okay.
No, thank you very much.
All right, thank you. At least now I'm sure that the microphone and all works. That's great. Shall we take a break before you move on? How much time would you guys want? 5 minutes, 20 minutes?
Yes, 15 minutes at least.
10, 10 please.
Okay, so it's now 10:30, so at 10:40 we meet again.
Thank you.
Okay, see you.
Thanks.
Thank you as well. Yes.
Recording. Okay, so machine learning, in all fairness, is not something really very new. But after the first presentation, that's probably not what you were expecting. Machine learning has been around since the 1950s and 60s. And the concepts that we had in the 70s, well, they still stand today. And the very simple techniques that we had then, we're still using the same. Minor improvements, maybe. But still, there have been major steps in the recent past. And those major steps, they come from probably not so much from the theory, but rather from the computers themselves. You see, the computers themselves, they suddenly got powerful enough. Of course, not suddenly, they grew to a phase that they are powerful enough to crunch more data. And so that simple concept that you can have, for example, let's take the essence of the brain, and these are neurons, synapses, neuron, and the neuron that is firing will kind of push the next neuron to be also in firing mode. And that concept is known as a coherent network or a neural network. And so neural networks, they are around from the 1980s, 70s actually. And the theory hasn't been changed at all, or slight improvements again, but the essence is still the same. But now we have machines that are just intelligent or just fast enough to make that simple technique doing surprising things. I mean, recognizing a letter, I programmed that at the university in the 1980s. You could teach a machine that could recognize the drawn letter A, for example, and then you have B and C, and you can build up and do optical character recognition, for example. That was one of the things around, but it was kind of silent. It is only when Deep Blue won the chess game, I believe 1995, that it really spoke to the imagination. Till then, we were actually kind of conjecturing machines are cool, but they will never be able to take over in intelligence or even creativity, because we as humans are way better than machines. But there was a small trick that changed the world. You see, a neural network was not new. That thing of having neurons that fire, that kind of push other neurons to fire also, that we had for years. What we didn't have was how to train the machine. I mean, we had plenty of chess-playing computers before that, but they weren't pretty good. At least they could easily win from me, but if you are a trained chess player, they stood no chance. And the reason why they could not win from you is very simple, because you had more imagination of what is possible. And so we tried to instead of programming the machine as we did in the past with programming the rules and then programming strategies and telling it if search, then do this. Well, we told the machine, well, okay, that is not how you're going to win. I cannot teach you to be a better chess player anymore. I will stop teaching you. You will teach yourself. Look, here are the rules. That is how you have a valid move, and that is how you win. In a complex world, we call that reinforced learning. So you don't tell the machine exactly what is good or bad move, but you let it do, and then at the end, there is some kind of payoff. The machine wins or loses. And then we told the machine, look, now you have some time for yourself. Go and play. Enjoy yourself. And of course, the computer did that 100 times, 1,000 times, 1,000,000 times, hundreds of millions of games. And from every game it learned something, maybe in an abstract way, but it fitted something what we now would call a deep learning network. So basically a neural network with multiple layers. We come back to that in a second. And the thing was able to win from the best chess player in the world. And of course, then we had these ideas. Oh, well, yeah, chess, it's a good game, but the Go is a more complex game. Well, we all know what happened a few years ago. The computer, and again, it was Deep Blue, if I'm not mistaken, won from the best Go player in the world. So now we are in a world where machines can do certain things better. So what I would like to do now is to invite you to my website in case you want to follow, or maybe not, because it's just sit back and relax. But I will give you a way to find back the code and to do the things that we're going through now by yourself. So I put in the chat box my website, and if you go to that website, it will have a page that looks more or less like this. It has some banner for the book about data, big data, and stuff like that. And you see, when you click on that one, it has a small table of contents at the front. And here is educational material. When you click on that one, you have per part of the book. So the book is organized in 40 chapters, and each chapter is grouped into parts. And we have something like 10 parts, okay, 8 or 9. And part number 5 is modeling, building models. So there is a lot more than what we will do now, of course. And here you have part 05.r, and that is the code. When you click on that, depending on your machine, it will ask to download or it will open this page. And so all the code that we will walk through sits here. So you can easily have that. Okay, that is just in case you would be interested. What I will do now is switch to a software which is called RStudio. The thing is RStudio, and that's basically an integrated development environment for the software R. It is pretty simple in setup in that sense that it has a few boxes. Sometimes there are 4, now I have 3 boxes on the screen. So what will happen is I have basically a text file with code, so I don't have to invent or retype everything at the moment that we speak, so it will be more fluent. Then we have a technical window, which is here, that will show the output of the code. And then most important for you is that will function more or less like a slideshow. So that box here will contain all the visualizations that we will just make on the fly. The reason why I do it in this way is not to make you all programmers, but to show how simple things can be done. And I hope in that way to make machine learning less of a buzzword, but something that you have a good understanding of what it can do and cannot do. And honestly, machines are really very simple at this point. We give them very, very simple mathematical rules, but the machine just repeats it a lot of times and it finds amazing results. Right, so the book itself is written to guide you through the whole data story. In that sense, from collecting data to extracting data to manipulating data to building mathematical models, from which artificial intelligence is a big part, and then to test the models and then to report on the models and build interactive websites and optimize your code and things like that. And to do that, we use a software which is called R. And so R is just the letter R. The environment that we will be using is RStudio. And so if you Google RStudio or you Google R, then you will find the things that we will be looking at today. It's a statistical language. So if you are familiar with languages like Python, well, it will be somehow be familiar. In that sense, it's a modern one. It's an interpreted language and it's object-oriented. Okay, these are technical terms, but that is what it has in common with Python, for example. Interpreted means that I have the engine here open and it looks ugly. But I can type things like, for example, empty cars. And empty cars is just, so I make the window bigger now, so nothing particular happens. I just click empty cars, and you see here is the output of that empty cars command. Okay, empty cars is not really a command. It is a variable that exists and that is basically a small database. And here, with the previous line, actually with that line here, question mark empty cars, I magically made that window appear. You see, that window has information about empty cars. So I will use this very small database to illustrate how simple machine learning can be done. And because it's only a few lines, it is very easy to learn. If you take the book or you have the code on the website, you can really do those things by yourself, experiment and adapt to what you want. Okay, so empty cars is a database about cars. It's reasonably old, but if you are into old cars, especially American cars, then of course it's a gold mine. It has only 32 rows, so there are only 32 cars, and it has something like 11 characteristics plus the name of the car. The interesting one is the first MPG, miles per gallon. You see the first column is miles per gallon. It has nothing particular, but okay, that is the one that we will try to predict based on the other ones. And the other ones are something like number of cylinders, displacement of the motor, horsepower, rear axle ratio, weight of the car, number of seconds to the quarter of the mile, the layout of the motor, the layout of the gearbox, number of gears, number of carburetors. Okay, maybe boring technical things or exciting things about cars that you always dreamed of. Well, anyhow, it's a very simple database and we can do easily some things with it. So one thing that you probably have, or quite sure have seen in a course about econometrics is a linear regression, isn't it? So a linear regression is where you want to fit a line. There is a line and you want to make it as good as possible. So in R, it works with functions, and a function is something that has a name, like, I'll try to make it slightly bigger so it's easier to read. Okay, so you have here LM is the function, and then it has round brackets, and then you have stuff between the round brackets, close the round brackets. So that calls a function LM. LM obviously stands for linear model. And then we have that small arrow here, which looks a little weird. It's like smaller than minus, but it's a small arrow. And that arrow will basically put the output of lm into a variable that we create at this point, lm1. So lm is the function, lm1 is the result of the function. That's how it works. Knowing that, you know enough to follow what is going on the screen. And so that first line basically just fits a linear model. The first thing, obviously, you just, in RStudio, you basically place the cursor in the line that you want to execute and then press Control Enter. You see here at the bottom, something appeared. So that is the output of that command. That is the output of my command, basically nothing. Okay, so this thing here is obviously the comment that I had here. So comment starts with a pound sign. Pound sign means to the computer, don't touch it. That is for me, that is not for you. So if there is a pound sign, the computer will do nothing with it. And then the next line, there is no output. That's kind of boring, of course, but you see when you do that, you can type lm1, which is now the variable, and it will give you information. Okay, so first it did fit a linear model. And what we did was fitting miles per gallon in function of horsepower. So we took just horsepower and we tried to predict miles per gallon. We do that in a linear way. So obviously what is happening now is that miles per gallon is predicted as a number times the horsepower plus another number. So basically I have a car and it has like, let's say 100 horsepower. Then I do horsepower times 0.068 plus 30. And that is my guess for the miles per gallon. So a car that has about 100 horsepower should have around, let's say 25 horsepower. Let's maybe have a quick look if that is possible. So I'm just make this window bigger. We scroll a little bit up and let's see if we can have a car of around 100 horsepower. Oh, here are a few around 100 horsepower. And indeed they have miles per gallon around 25. So it is not too far off. So the model kind of works. Obviously, you would say it works because that's honestly what is just going on. So basically, what we have done now is we made predictions and then we tried to make the difference between the predictions and the real value as small as possible. And you probably have seen in your econometrics course that mathematically what you do is you do prediction minus outcome, and then you square them so that they're all positive, so that underestimation or overestimation both are big numbers. And then you say, well, the sum of all those squared differences, we will try to minimize. That is the OLS, ordinarily least square. Now, the cool thing with that particular linear model is that there is an analytical way to solve it. You can write a formula in another way. So in other words, you can just write the formula. You do not need magical machine learning. And that is why we tend to think of linear regression as not machine learning. However, you can think of it as machine learning, but let's first try to plot it a little bit better. So the next line here, plot. Okay, let's again see what that happened here. So plot is a standard function. You see the round brackets. And what it does, it takes the horsepower from empty cars, and you see it writes empty cars $horsepower. And then it takes the miles per gallon from empty cars, colors that stuff in red. So these are the dots. It adds a title and some other colors. And then it also adds a line with the function AB line, and it does that in blue. And so the result is here. So basically we have the independent variable horsepower and the dependent variable miles per gallon that we're trying to predict. And so the linear model works as such that this distance is taken into account. We square it and we sum it with this distance, with this distance, with this distance, and all the other distances that you can make. We square them, we sum them, and the sum of all those has to be as small as possible. So you can find an exact solution of that. And that's why we don't call it machine learning, but honestly, you can ask the machine to do something as follows. Say, look, here is all the points, you have them, and now fit me a blue line, take a random one. For example, just take any point randomly, for example, this, and fit me a line through that one. And then, okay, now you wiggle the line a little. Let's say try this one and try this one, and see which one is better. Obviously, that will be the winning one. You use the same norm, of course, the sum of squares, and you will find this one is better. And then you're starting with that line and you wiggle that. And at some point, it will converge to the blue line. And then, ladies and gentlemen, you have machine learning. So already your linear regression in some way is machine learning. Okay, so now we can make that concept a little bit more complex. You see, the first thing was we had miles per gallon in function of horsepower. And so that was written as mpg tilde horsepower. We can make that concept a little bit more interesting by adding more stuff. Mathematically, not much changes. And okay, the way you write your solution is different. And so probably you called that multiple linear regression or something like that. But what it does is basically fitting parameters now, not only for horsepower, but also for number of gears, weight, cylinder. And actually, since the horsepower worked well, maybe we can just add it here. Let me do that. And then ask summary, and summary will give me this. So the formula is miles per gallon in function of horsepower, gears, and then you have cylinders and automatic manual taken together. Okay, that's maybe a little bit technical, but you see what it does is multiplying those variables. So basically you have a new variable, number of cylinders for automatic cars, and a new variable automatic for manual cars. Okay, so that doesn't seem to be very important. You see, you get immediately this kind of stars. So the intercept, well, that is, the intercept is here, the 30 miles per gallon without any information. So that is basically the average miles per gallon. That is significant. The only other one that is important is weight. And so my horsepower that was so important is gone. The reason why it is gone, again, is technical. It is because it is too much correlated with my horsepower. And so what I should do is leave the horsepower out. And try again, summary, and just make that window bigger. Okay, now it is slightly better. I have more stars and I have even a few dots. The dots basically mean it is not super good. You don't get a star yet, but it's kind of useful. Whereas this thing, number of gears, has no stars, so I can leave it out. Again, that's technical, maybe not so important now. So you can make that concept larger. The downside is you can't make a nice drawing like we have on the right side here. Of course, you can do many different things still to see how good the model is. But let's have a look at something we call decision trees. Now we start the domain of real machine learning. You see, in this particular case, when we asked our NT-cars data set on the screen, a little bit smaller and it will just fit. A decision tree will basically get the all data. We tell to the decision tree, well, find me the miles per gallon. And you can use all the rest. And then the decision tree will have a very, very simple rule. It will basically check all the things that we have, all the columns, cylinders, displacement, horsepower, rear axle ratio, weight, and so on, all of them. And for all of them, it will do the same thing. It will check what would happen if I split the database of number of cylinders into here, or here, or here, or here. Of course, it will order in the first place. The things are not ordered now. But so, for example, it would split the cylinders separate, so it would have the 6 cylinders separate, and then all the other, or more than 6, so the 8s, they go in one bucket, and the ones that have no line, they go in the other bucket. So we have the 6 and the 8 and the 8, 8, 8, 8, 8. We have another 8 cylinder. And so those cars, they go into one bucket, and the other cars go into the other bucket. So the ones with the red line are in one bucket and the others in the other bucket. And then we calculate the fuel consumption on average in one bucket and in the other. And then we try another split. What happens if I take the border of 5 cylinders, 4 cylinders, 3 cylinders, 2 cylinders? Okay, that stops to make sense, of course, at least in this database. And so for each column, it will try every possible split. That's quite a lot. But you see, it's stupid, simple rule. But the machine will do it a lot of times. And it will try that for cylinders, for displacement, for horsepower, and then it has this massive array of possible splits. And for each of the splits, we calculate how diverse the two groups in miles per gallon are. You need, of course, some measure of diversity here, but in that particular case, because it's just a number, we can just use standard deviation. And that's something we all know. And in that particular case, you just look the smallest standard deviation of your two groups. And for example, it is horsepower that wins. And the split is, let's say, around 100 horsepower. So the ones that are smaller than 100 horsepower are in one group, and the ones that are bigger than 100 horsepower are in the other group. And then it continues to split all the other columns as a whole, or the splitted column as a half part. Then it will try the ones that are more than 100 to make another split. The ones that are lower than 100, also another split there, and compare that with all the other columns that it already has. And it takes the best split. So again, very, very simple rule. Extremely simple. Stupid, simple. And in R, so basically what you have to do, so that is not, so the linear model is part of the standard offer of the software. Decision tree is not. So you have to load in a library. The library is called rpart. I loaded in library. So the first time that you do that, you have to install the library rpart with the command install packages rpart. Okay, I won't do that now because it will overwrite the package that I have. But the first time you do this, it will automatically copy something, download on your machine, compile if necessary, and it's ready to run. Next time you just load it. And loading is with that library here, and I do another library just to have nice plots. And then typically in R it's quite simple. You have a library rpart which provide a function rpart. And that function rpart works pretty much in the same way. You provided a formula which is written in some kind of symbolic way, miles per gallon, in function of all the other things. So here you can only use pluses because the type of things that this multiplication did, like combining stuff, that is actually automatically part of your decision tree. So you kind of should always know what you're doing, obviously. And you tell what data you want to use, empty cars, and a lot of technical stuff for your decision tree. Not important now, but we can fit our tree and we put it in the parameter t. And now we have our decision tree. Okay, so you can do different things, print the decision tree, rather complex output. So let me, okay, so it basically tells you how the splits are done. So the first thing is it splits according to weight, and it has found that the split at 2.26 is optimal. And then it gives some information about what is happening there, and the legend is here. So the next thing is there are 26 numbers, sorry, cars, and then there is the deviance, the Y value, the average consumption for the cars that have a weight bigger than 26, and so on. But it doesn't look very nice, so let's not waste our time on it. You can, of course, do summary. Still doesn't look very nice. You see, it's still kind of ugly and convoluted. Why don't we try to plot it? And I plot it right away with a nice package, and now we see what it is doing. So basically what happens, it tried all possible columns, and it found that it ideally should start with weight. That weight has the biggest impact on predicting the miles per gallon. And the border is 2.26. The cars that are bigger and the cars that are smaller. So for the cars that are smaller, it found basically that that was not necessary to do anything more. And I predict that they have 30 miles to the gallon, and I have 6 cars like that. However, the cars that have a heavier weight than this, it found that it was useful to split according to cylinder. The border is 7. So, and 7, you see where it comes from. We had 4, 6, 8 cylinders. So 7 is just between my 4 and 6 cylinder cars. So basically, here are my 4-cylinder cars, and here are my strong cars with 6 or 8 cylinders. For the 4-cylinder cars, it splits according to displacement of the motor. So that's the cubic centimeters of the motor, or some cubic decimeters, I guess, here. And again, we have a prediction. And so you see what it does. It finds that the cars who have a weight bigger than 2.26, 4 cylinders, and then displacement below a threshold of 153, that it predicts a miles per gallon of 22. So the prediction of miles per gallon is actually constant. So obviously, for predicting something like miles per gallon, which is just a normal linear function, it's not optimal because it will always go in steps. Each bucket will only have a step, a constant. And so that's basically all. Now we have our decision tree. Of course, there are many technical things that are interesting. Basically, what you do with such a tree is you try to grow it too big. And that can be, for example, overfitting, and maybe you shouldn't conjecture that on more cars it will still work. And then you can make it smaller and print again. And that is actually the only thing which is really relevant. So while the previous plot worked perfectly well for the data that I have, so if that is all the data that I ever will have, that's the best model. But if I want to use that to predict stuff on new cars, then this is the way to go. Okay, sorry, one technical question before I move on. At what time do we want to finish?
12:30.
12:30. Okay, lovely. Thank you so much. But so the problem with decision trees is somehow that they overfit. So you see this is the only relevant thing that I can get out of it. That's not super powerful. Because the other thing that I've shown, the previous plot, the more complex one, this one, that one is actually only valid for the small data set that I have. I can't really use it to make predictions. Probability to make a mistake is too high. So it overfits in technical terms. So another way to do that would be to say, no, a way to solve that problem is random forest. Okay, random forest is an entirely different technique. And random forest basically is mostly used with decision trees, but you can use it for anything else. And so the problem is that if you would just add one car that can change the top node, and that can, for example, make sure that you don't have weight here anymore, but that you have something else. And then because you don't have the split around weight, for example, cylinder pops here, then all the other things will be totally different. So a decision tree is very sensitive. You change one thing and it can look completely different. That's really annoying. Mathematicians don't like that. It is an unstable model. And if you want to use it in banking, you're in very bad paper because the regulator will challenge you on that. You just have a few new customers and the next month you have an entirely different model. Nobody likes that. Makes everybody nervous. And of course, you can prove that predictions are more or less similar and things like that, but nobody will like it when it changes too much. So what if we try to fit 1,000 trees? And in every tree, we do something slightly different. For example, we fit a tree in which we don't have the column cylinder. And we leave out randomly, just like this car and this car. That is something that we can do. You see, there are two types of randomness here. First of all, we decided to leave out the column cylinder. So this is out, and we leave out some rows. And then the next tree, we can do something else. Randomly, we leave out this column, and we leave out this and this and this line. And we do that 1,000 times. Okay, then we have 1,000 different decision trees. That's kind of annoying to make predictions, of course, and it is hard to see the trees through the forest. I mean, it becomes a big chaos, but that is what you see when you look at the forest. You can't really see all the trees, isn't it? You just see a bunch of stuff. And now we have a bunch of trees that all are slightly different. But okay, let's now do it a little bit smart. We can use every tree to make predictions and just let them vote. You see, every car can go through that cascade. And for example, for this tree, we predict miles per gallon, 13.14. And then we have another decision tree and we have the same car. Okay, so, and we predict something else. For example, we predict 15. And so what happens is that for each decision tree, you have a different prediction. So you have your 1,000 trees, all with slightly different columns, all with slightly different rows, and they all make predictions. And just give them each one vote. Democracy. And that we call random forest. So random forest, as usual, you need a library which is called random forest. You have to install it with install packages first, but then you can just load it with the command library. You need a formula and you need your data, and you have a function that is called random forest from the library random forest, and that will fit your model. Now, the problem is here, well, I can't really make a beautiful drawing like this. You see, and that is the big advantage of a decision tree. It is simple, it is lovely, it is understandable. Humans have been using that before we had the concept of decision trees in machine learning. You can use it for everything. For example, you want to cross the street. Is these white lines? Yes, then you have to use the white lines. If there is none, then you have to look left and right. And if there is a car, then you stop. If there is no car, then you can go. This comes natural for us. Random forest, well, we can't really represent anymore. And so print random forest obviously will tell me just some information. I have been fitting 500 trees, but I can't just show you the 500 trees. That wouldn't make any sense. Well, I still have the command plot, but you see the plot does something weird. It tells me in function of the number of trees that I was fitting, you see the error in the model. So the deviation between the prediction of miles per gallon and the realization of miles per gallon, that went dramatically down. So we did win some stability, but more than 100 trees probably doesn't change much. It's a small data set, so that's no surprise. So you can't really represent it anymore, but because of the voting system, you can actually make predictions that are more stable. And now you can predict stuff that is not part of your database. You give another car and it can predict the miles per gallon in a more reliable way. Okay, these are more technical things, so I will skip those. And now the neural network. So the neural network, already we agreed what it was, isn't it? And I will just use the white canvas here to make some drawing. Our brain has different neurons. Of course, they are layout in 3 dimensions, so I can't really draw it. And the neurons, they are in firing state or non-firing state. For example, firing is red. Firing means basically stimulating others to be also in firing mode. Whereas the non-firing ones, they are passive and they don't push others to be firing. Then there are synapses. Synapses are connections between all different kind of neurons. And each neuron in our brain has around 10,000 such connections. I only draw a few here. And so what is happening in our brain is that this neuron here gets input from all the other ones. In this particular case, it only has 3. And so basically what happens is that this one is not firing, so it isn't pushing anything. This one is not firing, so it doesn't push anything. This one is in firing mode, so it will push this one to be firing. So my neuron A basically sees an input only from this one. And so in that neuron, we basically have something like a curve that tells me what to do next. And that is more or less like that. If the input is small, then it will do nothing. And at a certain point, it will also get into firing mode. And so here is a cutoff. If it gets over that cutoff, it will also be in firing mode. So for example, this neuron only gets input from this one. And let's say the input is here, so nothing. It's below the threshold. So nothing will happen. And then 100 times per second, so 100 hertz if you want, compare that to the computers with 3.5 gigahertz, our brain recycles through everything. Now imagine that this neuron here, because of all the other inputs that it has, is also in firing mode. Then our neuron A will see input from this and this. And basically, just like in a linear regression, it will say 1 point here, 2 points there, and this one is maybe more important and it gets a lot of points. And you see, we end up here. Oh, sorry, it should be a little bit higher. And so it is above the threshold. And so it will also be in firing mode, which might then influence others like this one, or maybe back this one, and so on. So a lot of things are possible. And that is actually a very simple way of working. You have different nodes or things or neurons, and they are connected with each other. And they basically stimulate each other to be in a state like firing or non-firing, open or closed, 0 or 1. Pretty straightforward, pretty simple. And that is how a neural network works. So let's try it in the first place on our data set of empty cars. So what we want to do is obviously install packages neural net if you don't have it. And the package neural net provides a function. Sorry, the package I have to load here, and then it provides a function neural net that can be used. That functional neural net takes a formula of the typical form, and you have to give it also a data set. All the rest are technical parameters for my neural network. And let me just do that. And now plot the thing, and that is how it symbolizes. So basically what happened, probably crucial here is this parameter hidden. And okay, it's a little bit strange way of writing it, but it's a column with just one element. So basically the number of hidden layers, there's one hidden layer with 0 neurons. So what happens is all my input immediately predicts the output. And so here we have that small curve with a threshold value. And okay, in the case that, okay, so it's miles per gallon. So in this particular case, it's a continuous parameter, so you don't need a threshold. You just predict the thing straightforward. And so you see what happens. Weight has a weight of minus 3.7. Number of carburetors has also a negative weight. Number of gears has a positive weight. Rear axle ratio has a positive weight. And so you put in horsepower, for example, 100 horsepower times this number here. So you get -2, and you have -2. Then you have displacement times this. For example, you have 5. -2 plus 5 gives you something. And then you do that for all the parameters, and then you have the prediction for miles per gallon. That is exactly the same as our linear regression. Exactly the same. If you will try those things on linear regression, they will, well, okay, fail for another technical reason, because linear regressions are sensitive to this horsepower being so much related to the displacement of the car. So linear regression will fail, but in essence, it does the same as this neural network. Neural network will not fail on it, but it won't be super stable either. Neural networks basically become more interesting. So these are the type of things that we always had around, let's say from decades around, but Deep Blue wouldn't be able to win just with that. What you need is multiple layers. You need more hidden layers. Here we have 2 layers, the first with 3 neurons and the second with 2 neurons. And that line of code will get us to something different. And we again fit a neural network, put it in NN1, and then we plot NN1, and wow, slightly different. Okay, let me try to make that big. But no matter how big I make it, it's kind of hard to understand, isn't it? So now suddenly we have so much more parameters. So we have 10 input parameters, and each 10 input parameters has weights on these nodes here. So you have 3 times 10, that's 30, plus your intercept here, which is the constant that has to be added in each of the nodes. So that's another 3, that's 33. And then you have all 3 neurons of the layer 1. That's the layer 1 here. And then you have layer 2. So if we look, in our formula, okay, it's just dropped off. The hidden layers, 3 hidden layers, that gives this line, this column, this row. That's our 3 neurons in the first hidden layer, 2 neurons in the second hidden layer, and that's this. And so we have quite a lot of parameters. And now we see immediately why neural networks are considered as black box things. For us humans, already now, it's not possible to understand what this means. I mean, is this something that tells me it's a muscle car? Well, it's really pretty hard to see what exactly is going on. Is it? We would go along concepts like muscle cars or city cars and things like that. Probably we get a better neural network. I know the database, and so I know that 4 would make more sense. And you can actually add another layer, like let's say 3, and then plot the thing again. You see it becomes even more complex, but this thing should have better performance. But now we also understand why neural networks are black boxes, because they have too much information for us humans to understand. So while the principle is really very simple, in every node you do exactly the same thing. You basically try to predict the miles per gallon, and then you try to make one of those things slightly different. For example, here we increase a little bit. and we see if it's better. If it's better, then we keep it. If it's worse, then we don't keep it. So we try something else, and we try this, and we try this, and we try something else. And that's how machines work. Very, very simple rule. And that simple rule allows us to optimize the neural network. And because of that massive amount of parameters, neural networks can fit about everything. Okay, there are many other things. And let me just show you something which is called k-means. K-means are cool because they are what we call unsupervised learning. You see, our linear regression, our decision tree, our neural network, they all were told, here is what you have to predict. I am the teacher. I will tell you what is good and what is bad. These miles per gallon, that are the good results. You can rely on them. Just fit whatever you do, your tree or your forest or your neural network, and do it in such a way that those predictions that I give you are as good as possible. So what now if we just ask the machine another type of question? We ask the machine, find me a way to group the cars so that they are as similar as possible. But I won't tell you what is good or bad. That is unsupervised learning. And again, the machine will do that in a very simple way. So imagine that, actually we don't have to imagine, we can just ask empty cars. And so basically what the machine will do is, okay, say let's take one car or one point, and maybe that's a car, maybe that's just an imaginary point, and say I want 3 groups. So I select, let's say, 3 cars. That doesn't have to be cars. It can be just empty points also. But you can, if you want, define a distance in a mathematical way between the cars. For example, this minus this plus this minus this plus this minus this. It wouldn't be a good measure of distance, but that's the concept. You have to square, and of course you see that these are big numbers and these are small numbers. You have to take that into account, but the concept is the same. Define me a distance to the car, and the distance is related on the difference in miles per gallon, cylinder, displacement, everything. And now I have 3, and then you can start with 3 random center points. And then you calculate the distance of all the cars with all the center points. And then you say, well, now I will allocate the car to that group, which is the closest to the center. So for example, we had a center here, and this Dodge Challenger is the closest to that one. And the Hornet is also closest to that one. So they go in one group. And then we had another group, say this round group, and Mazda was closest to that one, and Duster is closest to that one. And it goes also there. And then we have new groups. And within that new group, we have plenty of cars, so we can again calculate something like a center. And maybe it is here, and maybe we have a center here. And then we restart. And so again, a very simple way of working, starting with random center points, calculating the distance, allocating the cars to the group which is the closest, calculating new center points, calculating the distance again. And you have some entirely new concept which we call k-means. Okay, what I do here is preparing the data a little. It's rather technical, but it doesn't really matter. A technical thing is that I want to get rid of bigger numbers and small numbers because this one is very sensitive to it. Here in the neural network, bigger numbers or small numbers don't matter. This coefficient will take care of it. Of course, if I normalize everything between 0 and 1, I can understand the coefficients better. A bigger coefficient will have a bigger impact. And now I don't know because miles per gallon was bigger numbers than weight, for example. This method, it is quite sensitive to it, so I have to normalize everything first. And now, okay, we have different clusters. And let me right away plot the things in a specific way. So I define colors per cluster, and then I use a maybe a little bit abstract library ggplot to plot the result. And I have chosen four groups of cars, and look how it ends up. If we just look at weight and miles per gallon, just randomly choosing that one, that's just one way, and they kind of nicely separate already, which is pretty cool. However, the true strength comes through having something in, let's say, a more mathematically more abstract thing. You can try to find new columns that are called principal components. Those new columns are perpendicular to each other. And what that means, they will maximize the distance between the different groups visually. And so, okay, I have two technical variables. Instead of weight, I have principal component 1, and instead of miles per gallon, I have principal component 2. And if I plot the variables, sorry, the observations now, you see that's really fantastic. Now the groups, they are apart. And now you understand why I took 4 clusters in the first place, because I already did that exercise and I saw that here was a cluster. This is probably the light sports cars. Here is another cluster. High displacement, high cylinders, high horsepower, high weight. Muscle cars. Oh, sorry, the light sports cars are here. So these are the city cars. And here are some other cars. And so that is actually so this is more of a, this projection, or the axis that I chose is quite analytical, technical, so not machine learning. The coloring of the groups is done according to the machine learning, and you see it makes sense. All right, the rest is just to improve the plot. I won't do that now, but that is basically what I wanted to explain. Of course, there are other ways of clustering, and hierarchical clustering works in such a way so that you can make such plots, and you have basically splits in 2 groups, and here you have the 4 groups, and then you see what the 4 groups, which cars would fall into. But there is finer hierarchy possible, and you can decide where to take the cuts, and for example, this could be one group of cars. So all different things that give you a little bit more insight. So with this, we went in a very fast pace through machine learning. No fancy theory about supervised learning and these kind of things, but in the end, we did it all. We started from linear regressions. From the linear regressions, we tried decision trees, we tried neural networks, and we tried an unsupervised machine learning technique, which is called k-means. Okay, before we jump to the quantum computing, are there any questions? Do we need a small break? Okay, that sounds okay. I hope that my microphone, everything is working fine. I don't hear anybody asking for a break. So let's continue. There is only like 45 minutes left anyhow. Okay, let me just try to find the quantum computer presentation. And share the screen. Okay, lovely. Good, so quantum computing. Basically, I hope that you can also see my image. I have here a deck of cards. And what I simply will do is take some cards. Let me just take these cards here. We have 3 cards that are black and 1 card is red. And when I would turn around the cards or just hide them so that nobody can see them, and I've asked you to find the red card, then you would probably, well, or there is a small trick, or you just would have to try all of them before you would find the red card. You see, in our world, finding the red card faster or always from the first try, that is or a trick or magic. But there is no science that can help us to find the red card right away from the first try. Or is there? You see, in our world, logic is very simple. If the cards are with their backs upwards on the table, you can't see through them and you can't guess which is the right card. Well, it is abstract, but quantum world is abstract. And in a quantum world, it is possible to guess the right card always from the first time, or almost always. And that is actually something that quantum computers will be able to do. So quantum computers, they really are able to do magical things. So the trick of the card is basically trying to invert a function. So the function is really very simple. It has 0 everywhere, except here it has 1. And so if I want to know what the red card is, in 1, in 2, in 3, or in 4, basically what I have to do is to invert the function, and then I will know right away it is in slot number 4. Quantum computers are able to invert functions without really knowing the function in the first place. And that is a trick in quantum world, which quantum logic kind of makes sense, but in our world, it never happens. It is weird, it is magic. And we tend to believe that magic is not possible, but magic is possible. We live in a magical world. Of course, magic that is obeying certain laws of the universe, but quantum computers truly, honestly, are able to do things that are part of magic for what we as humans are concerned. We know such kind of things for more than 100 years. We know that quantum effects exist. And quantum effect, for example, tunneling. Tunneling is what underlies a transistor with a silicon-based transistor. So in our computers, those things, they have 3 billion transistors, which are based on quantum effects. And the effect is such that the current can go through in one direction and the other direction not. And in our world, if you want to cross a mountain, you need energy to get over that mountain. And if you don't have enough energy, for example, you don't have enough diesel in your truck, and then you just can't get up the mountain. You don't even have to try, it won't work. Imagine that your truck needs 5 liters diesel to get up the mountain. You only have 4, you're not going to get there. Never, ever. But in the quantum world, magically, sometimes the truck just appears on the other side. That quantum effect is called tunneling. We know such effects, but we tend to believe that they are part of the microscopic atomic, subatomic world, and that in our world, we will never see anything magically appear on the other side of the mountain, because that would be magic. Well, the thing is that quantum computers bring those magic to, let's say, the information of that magic to our level. And it's truly remarkable that that is possible and that we will be able to witness such things. So quantum computers, they do something different than classical computers. You see, a classical computer is a Turing machine. A Turing machine basically takes input, and you take that input and you throw it into the machine. The machine has algorithms, and to those algorithms, you create a certain output. And that output, well, you can design random algorithms, but you will always understand what happens. So basically, our random forest I explained how the algorithm works. You take all the data, you look at all the columns, you look at all the possible splits in all the possible columns, and you split on every possible split. And then you see which groups makes the most sense, which groups predict you best the miles per gallon. See, that is the algorithm. It works always in the same way. That is what we call a Turing machine. We have quite great Turing machines on this planet. Here is, for example, the Fugaku. One of the best ones. There are now, I think there is a bigger one already at this place. Every year there is a new one. These things, they do magic. In that sense, they can do things, a lot of things. So this one does, 442 petaflops. So that is 442,000 billion floating point operations per second. So 442 million millions floating point operations per second. And that it does that because it has so many. In all those boxes here are servers, and all those servers, they have multiple processors, and all those processors have billions of transistors inside, and that's why that thing is able to do so much calculations parallel. But it is all deterministic. And one of the beautiful things it can do is you give it a large number, so read that as just one large number, multiplied with another large number, and it does this. So I quickly created a program in C++ to do that thing. It took me half an hour to program. It runs in less than a second to do this long calculation. At least if I ask it to do it in this direction. If I want to go from left to right, it goes fast. If I want now the opposite, if I would start with this number and ask you, which prime numbers do I need to multiply with each other in order to get this large number here? That's an entirely different question. There are algorithms that are slightly better, but not knowing those difficult things, you would just have to try all prime numbers. You would have to try 3, 7, 11, and so on. And you would try all the prime numbers. But you see, this is billions and billions. So before you're on this number, you have to, first of all, know a lot of prime numbers and then try them all. So going from right to left is very, 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 very slow. That logic underlies something that you probably know as PGP, pretty good privacy, or HTTPS, secure hypertext transfer protocol. So any banking transaction, any online purchase uses this logic. If you encrypt your hard disk for whatever reason, you use this logic. In our world, going from right to left is pretty difficult. There is no simple way of doing that. And so if you ask a supercomputer to do that, the supercomputer will do its best. But you see, if you give it a simple thing, like 10,000 digits, so 10,000 digits here, it does it pretty fast. If you encrypt with 10,000, no match for Fugaku. 100,000, no match for Fugaku. Well, at least you need some importance of the message in order to have that machine working half a year and crack your password. But okay, so today we use 256,000 characters, and that's we're here. So with the encryptions that we typically use on the internet, a supercomputer would need 80,000 years. 80,000 years of hundreds of thousands of watt consumption, best computing power in the world, no way we're going to spend so much resources on cracking your password. And by the way, by the time that we crack your password, you're gone, so it doesn't matter anymore. So the lesson here is that we can easier increase the complexity of the system than the computer can easily solve it. The difficulty of going from right to left scales different in the computer than the number of digits. In summary, what happens is that the number of digits can easier scale, whereas this scales exponential. So I'm telling you now that there are special machines around that, or almost around, that should be able to do those things in a very, very different scale. So I made some simulation here, and quantum computers, you see, when there are little numbers, in this particular case, they're not efficient. But the scale is very different. Whereas if I would use 400,000 digits, supercomputer would need 72 times the age of the universe. My quantum computer would do it in 3 minutes. And that is why, if we are able to build quantum computers with that capacity, then none of our encryption is safe anymore, because quantum computers can guess in 3 minutes the password. And so any transaction on the internet, any Bitcoin, any blockchain, any secure connection over Internet of Things, quantum computers will decrypt it. So we need a different way of encrypting. Fortunately, quantum theory gives us another way, but that is not yet ready to be used. And so you see how it scales in quantum computers. The complexity goes up very slow in function of the number of digits. Whereas in a classical computer, it scales exponentially or near exponential, meaning that you will hit a wall somewhere, meaning that it is easier to increase the complexity of your encryption key than it is for me to increase the capacity of my computer. So I'm lost. If you want to use that encryption, I cannot scale my computer fast enough, because you can easier encrypt more difficult things. So this is what quantum computers can do. But what are quantum computers? Well, honestly, quantum computers are just the universe. I mean, look at water. Water is a very simple structure where you have something like an oxygen atom and 2 hydrogen atoms. The hydrogen atom has 1 electron, and the oxygen one has 8, if I'm not mistaken. So 2 are drawn here on the outside, but there are others that are more on the inside, and they're not drawn. So in total, you have 3 positively charged particles and 10 negatively charged particles. And somehow they hold each other together in such a structure that they don't fall apart. Well, the thing is that if we want to use a supercomputer like Fugaku, then it is impossible to solve it. That problem of simply 13 moving particles is way too complex for Fugaku to solve. The reason is that you have so many possibilities for this thing to move, and it is based on the position of all the other particles that are in your system and how they are moving. And so the possible interactions, the possible combinations is way too high. So that is our world. We try to understand water and we fail. However, if you look around us, water is everywhere. And if you have a motor that burns hydrogen, well, it creates billions of water molecules every second. So the universe has no problem creating water. We have a massive computing problem if we want to create it theoretically. And so that's the difference. Our world is the world of simulation and logic and Turing machines. The quantum world has no problem of creating water. In the quantum world, it just happens very, very, very fast. Some things even outside of time somehow. So fast. And so, if we can harvest the power of nature and use those quantum effects to our benefit, then we have what we call these days a quantum computer. So a quantum computer is actually more basic than a Turing machine because the algorithm is just nature and we have no much influence on how nature works. And so all the strange effects of the quantum world, we will get to our world. For example, you probably have heard of something which is called the double slit experiment. It is one of those things that illustrate how strange the quantum world is, how impossible the logic of quantum world actually is. You see, if you would have a screen that is not transparent and you would have two openings in it, so there is a slit here and a slit here. If you would take balls and throw them through it, then you would have on the screen, I draw it a little bit higher here, let's say balls that end up on different places. And you would basically have balls here and here. For example, paintball. If you do that with paintball, you would, and you have the screen with two openings here. With your paintball system, you can have two places where the balls end up. If those openings are big enough, then your places will be big and they will somehow overlap. And then the probability of having some stuff in the middle is always higher. So you can have this kind of distributions. The point is that they can never subtract from each other. If you have paintball happening in one place and you add paint from another ball, it literally adds paint. It's not because I have a blue paintball and then I add a red paintball that the paint just magically disappears. There is just more paint, doesn't matter the color. They add to each other. That's how it is. In the quantum world, it's very different. You see, but that thing is not so strange. For example, if we have water, imagine that this is a box of water, an aquarium, for example, and we're looking from above, and we have a screen with two openings, and we have a block here that we move up and down, and that thing will make longitudinal waves. And they're stuck at the screen, but there are two openings. And so those openings will create waves like so, and those waves will interact. And you see there are places where the waves are subtracting in red, and then places where they are adding to each other. And here at the screen, you will have interference pattern. You will have density, which is something like this. Well, it is drawn better on the screen here. So here you have an interference pattern. Instead of two bars, you have multiple bars. That is only possible for waves. And so the first time we did such an experiment 100 years ago with photons, we saw this coming out and we said, oh, Newton was wrong. Light is not particles, light is waves. And then everybody believed that lights were waves. But then we were able to single out one photon and we let it come through. It landed here. And another, it landed here, another here, another here, another here, another here, another here. And we saw for the first time in front of our own eyes an interference pattern being built up based on particles. Again, that is something which is absolutely crazy, absolutely impossible. In our world, there are two things. There are things like cards, and there are things like waves that you could make in water. You have no things that are both waves and particles at the same time. However, photons, electrons, or other small stuff. They seem to be both. And in a very particular way. Quantum physics is such that as long as I don't look at the electron, photon, or whatever I have, it behaves like a wave. At the moment that I make an observation and that screen functions as an observation, it just materializes as a particle in a point somewhere. Before that moment, its position is described by a wave. And that wave is going through both of the slits. And that's why you get that interference pattern. But at the moment it hits the screen, it materializes in one point. Let that sink in for a second. While, okay, you logically can understand what I'm explaining here, it is honestly totally absurd. It doesn't make sense in our classical world. So whether I call it magic or not, the quantum world is weird. The quantum world is different from our world. And so things that we knew happen on microscopic scale, we tend not to use them, or tend to think that in our world it doesn't make sense. Although these things, again, they have quantum effects inside them. If you have ever walked through something that's infrared scanner, maybe your garage door even has such a thing, that when you're closing the door and somebody walks out and the door will stop moving downwards and go back up. That works because photons are passing on from one thing to another thing, and that other thing that percepts the photons will interact in a very particular way with the photons. In quantums, in discrete packages, not as waves. And that is only possible because of quantum mechanics. So quantum mechanics are a big part of what's surrounding us already. Or just let's think about this thing. That is just a plant. And we all know that on our planet, plants are generally green. Plants are green because they have something like chlorophyll, and that is used for photosynthesis. Photosynthesis is used to basically use photons from the sun and store energy in a form that we call sugar. And that sugar can then be burned again by animals or plants that come in a higher degree and do something with it. First of all, this plant will use that to produce energy for itself. Okay, this one is not very good to eat, but other plants are eatable. And you can basically harvest that energy. It's quite interesting philosophically, because at the moment that the universe started, the amount of energy and matter contained was given. So the moment after it, no matter how small the moment you take after the Big Bang, the amount of energy was finite. Unless the thing is, of course, infinite, but okay, we don't know that for sure. What we do know is that there was a certain amount of hydrogen, and that hydrogen is a thing that is fusing in the center of our sun, like in a nuclear fusion reactor. So we have that massive nuclear reactor close to us, and that is the sun. And that sun is burning the hydrogen that was formed at the start of the universe, creating helium, and in the process, heating up the photosphere of the sun, which then sends photons to the Earth, which warms up the Earth. And one of the major mechanisms is that plants capture that sun, transform it into sugar, and makes that whole variety of life possible on our planet. Okay, so far so good. But photosynthesis as such is not possible in classical logic. You need quantum mechanics to make it work. Because basically what happens is that a photon falls from the sun and hits an electron, and it pushes that electron to some, let's say, higher state. which stores the energy difference, and that energy difference can then be used later. Well, there are multiple problems. First of all, the photon as such does not have enough energy to push the electron to that state. Remember the story about the mountain? In our world, if you don't have enough diesel to pull your truck over the mountain, don't try, you're not going to get there. But the photon will try anyhow and succeed in some amount of times. It can tunnel through the mountain in some way. It can get to a higher energy state and actually doesn't really get enough to do that. But there is a certain probability that it gets there. Plus, in the meanwhile, it has to navigate a labyrinth of other possible states, and actually it doesn't have enough time to try even a millionth of it. So there are two things that make photosynthesis impossible, and yet it happens. It is the main trick that is going on our planet for more than 3 billion years. And that is possible because of quantum mechanics. You see, in quantum mechanics, first of all, it can tunnel through that energy barrier. And second of all, it can navigate all the possibilities of that labyrinth at once. Or if you want, in different realities. And then at some point, it just materializes in the place where it was. So quantum computers try to harvest these type of phenomena. As such, they are not more than just simulations. They are not Turing machines that you can program with an algorithm. You basically just set some initial conditions and then close the box, don't look at it, definitely don't look, and then open it in a smart way and you will see the right solution. Things to simulate are not new. Remember the ENIAC, that early computer? Well, Enrico Fermi, one of the famous physicists, was using it at some point to make simulations about how neutrons transport into crystals. But ENIAC being ENIAC, it needed some time to be repaired because there was a bug inside, and one of the real bugs had to be found, and some cathode lamps needed to be replaced, so the machine was down for a few months. In the meanwhile, he needed his simulations because he was just stuck on his own research. So he built this small trolley, and that trolley would be put on an inclined plane, and it would be allowed to drive down the plane. While it was driving, certain stuff started to move, and you put a small marble on it here, and that marble would roll off in a certain way, fall, and then that would somehow simulate the reality of the movement of neutrons in the crystal if his theory was right. And so quantum computers do pretty much the same. They simulate certain things. And if we can make an abstraction that is good enough, we can harvest that logic for our world. The type of thing that we need is something that we tend to call qubit. Remember, in computers, we have transistors. We have transistors that can be 0 or 1, open or closed. And so in the quantum world, it's slightly different. So the closest that we get is something like, for example, spin. Well, electrons don't really turn because they have no dimensions as far as we know, but they have a mathematical property, and we call it spin. There are other things like magnetic momentum. There are other things like color, charm of quarks and stuff. They're all basically just numbers. In the whole universe, there's nothing real except numbers. There is nothing like softness, elegance, attractiveness, or hardness at the microscopic scale. You see, if you have something which is hard, like this pen, for example, it is hard when I touch it. But basically, if you try to understand what that hardness is, you look down and you see that basically the electrons of my finger are pushed away by the electrons of the pen. And so while I'm pushing that pen, and I will say, well, I'm touching the pen. No, I'm not. I'm not touching the pen. because the electrons of my finger will push away the electrons of the pen, and that is that pushing back that I feel, and basically the electrons do not touch the pen. Okay, and then you try to understand where these electrons come from, you have the atoms and stuff like that, and then you see that in the end you end up with stuff like this. And there is nothing like softness or hardness or elegance. There is just numbers. And one of those numbers is spin, and so you can have electrons with spin +0.5 or -0.5. However you measure, you can measure along the z-axis, x-axis, or y-axis. And depending on the initial conditions, there is a certain probability of finding it as along the y-axis. And when you measure along the y-axis, it can be +0.5 or -0.5. And as long as you don't measure, it is basically in some weird state, an in-between state. It's not really unknown, it is basically all of them together. You remember probably Schrödinger's cat? That is what I'm trying to explain here. And okay, the parable of the cat is of course invented to show that the quantum mechanics was too weird and couldn't be possible. But no matter how weird it was, we found out that it actually is like that. Before you measure, it is in all states together. It is a wave, it is a function, it is a wave function. And the reality corresponds to complex conjugate of the, or somehow the square of the complex function. So complex numbers don't even make sense in a complex function, and then you square it, and then you have the probability distribution. Really weird. It doesn't make sense. But okay, that's how quantum things work. Now we have a small tool. We have something. Let's say it can be plus or minus, and I will measure along the z-axis. In the meanwhile, it can be everything. So it's very, very different from our 0 or 1 gate. This is a gate that is, when I measure, it can be 0 or 1, or I can measure along other axes. And it can also be 0 or 1. In reality, it is nothing as long as I don't measure. If I then have multiple of those things that are connected with each other in a mysterious way, that connection is also very important. And that connection is basically something that also happens outside of time. So it's really weird, because one of the things that Einstein never accepted that could possibly happen. But again, as long as we can test, these type of connections exist. So you need that special connection, you need a special qubit engine, and now we are ready to go. If we have enough of those things, we can put them together and do something useful. For example, here we have a Canadian company which is called D-Wave. And D-Wave is building these massive fridges. They started off selling them 20 years ago for, I believe, $25 billion, and now they're down to around $10 million. So they become reasonable to buy. The processor is this. And the whole fridge is basically a mechanism, well, literally to cool down the thing. Because you see, those quantum effects are very fragile. We're talking about the orientation of a single electron. A single electron, spin up or spin down, or a single atom or an ion at magnetic moment or something like that. And we all know that temperature, like hot coffee and cold water, what makes them different is the movement of the atoms in it. In hot coffee, atoms move faster. So heat will just basically disturb that quantum effect and makes it impossible to see anything through it. So you have to cool it down. And they cool down their machines to minus 272.73 Celsius. So almost the absolute zero. Something like 1,000 times colder than interstellar space. So the coldest places in the universe, by our knowledge, are inside those fridges. And that allows us to read out certain quantum effects. Now, what D-Wave is doing is something what we call adiabatic annealing. Adiabatic annealing is probably best explained with some kind of landscape. You see, when you look at the landscape, that's actually a picture of their website, so you can do the reading yourself if you want. If you look at such a picture, then if I ask you, show me the lowest point in that landscape, well, you probably have some impression that here within a mountain we're going down, and probably here is going to be lower, isn't it? And then definitely the lowest place should be somewhere under the water. We don't know how deep that lake is, so maybe let's check it out. So you have some obvious way to start. But ask that to a Turing machine. Ask that to Fugaku, for example, or Sumit, IBM's newest, fastest supercomputer. And then you will realize that that machine has to scratch his or her figurative hair and won't really have a good way to start. That machine will say, well, okay, let me try. Well, of course, you have to program that algorithm some starting points. Okay, let's first try with just one. And then from that starting point, I look around me. I look in this direction, this direction, this direction, this direction, and I see where it is deeper. Oh, this is deeper. So let me look around from here and try to see. And now the deepest point is here. And I get stuck here. Okay, so that's the deepest point. Now let me try a random other point here and move from that point, and I find that the deepest point is here. Now let me try another point. I find the deepest point is here. And so you can try that 1,000 times, and then you probably, hopefully, have found something reasonable. So that is a classical computer. That is something we can understand, that algorithm we can explain. But now imagine a quantum computer. And actually, you don't have to imagine it because D-Wave already does it somehow. And basically what we do is we program that landscape in that computer. So that processor basically allows you to program that landscape. Now we have the landscape programmed, and now we ask the computer, show me the deepest point. And it does that very much in the same way as the magic of photosynthesis works. Remember the small labyrinth that was there. Actually, when you close the process, so you program the processor and then you close it for a second or a 10,000th of a second, and you don't look at it. Do not look at it, because otherwise quantum mechanics will be interfered with. And then you open, and magically it's in the right place. And so, for example, you do that once, and it appears here. You do it a second time, it appears here. Third time, it appears here. Fourth time, it appears here. Fifth time, it appears here again. And then you say, well, okay, it ended up 10 times here, once here, so the right solution should be here. And that is how a quantum computer does that for us. What happens in between when the box is closed, that is, of course, magic. There is no other real word to explain it. So you can explain, well, it opens up different realities, and in each reality, it tries a different solution. So it opens up 1 billion of new realities. And then when you look at the thing, it will just collapse to the reality that is the best. You can say, well, it tries everything at the same time, somehow with a certain probability. Well, anyhow, you get the picture. I can't explain it. And who was it again that said, if you think you understood quantum mechanics, then you clearly haven't understood it. I think it was Feynman, or I know. Okay. So that is how D-Wave allows to do optimizations. And now think of it as an investment portfolio and risk return, risk reward things, the mean variance algorithm that is already around since the 1950s. We cannot do, in any classical computer, we can't use too much assets to optimize the portfolios. Well, here we can have massive optimization capabilities. Last week or 2 weeks ago, Goldman Sachs had an absolute breakthrough with quantum computing, where they were able to optimize a reasonable portfolio using a quantum computer. But honestly, it's still limited, but you can do a lot and more abstract things. What we see here on the screen is a F-35. It is an absolute murder machine, and it can kill with high precision, and it can destroy with high precision, and it can do a lot more. It can, for example, land on a boat during a storm while the boat is heeling and moving and rolling, and while gusts of winds are coming and going because there are high waves, and the thing can just land in a spot, and exactly in that spot it doesn't need more place just to sit on the boat. That is something that we as humans can't even risk to start, but that machine can do it. It can do that because of a lot of computer code inside. Of course, if you have millions of computer lines, you will have mistakes. And the problem is, of course, finding those mistakes. Now, if you are building an accounting software, then you just ask some accountants to test it for a while, and then you try it for real in a company. And if something goes wrong, you solve the problem, isn't it? Well, with this thing, it's more sensitive, because if you are going to make mistakes, then you will kill people. Plus, that thing as such costs a lot of money. So you want to avoid that. And so you can hire an army of consultants and run through your code and try to debug the code. But what they tried a few years ago is buying a machine of D-Wave and kind of programming that landscape, finding the computer mistakes in the software of that machine, and they solved it in a few weeks. That was actually amazing. So there are real applications for quantum computers already around. But what for you probably matters more is, well, buying such a fridge of D-Wave, well, first of all, it will cost you a lot. It will cost $10 million at least. The second thing is, it can only do this one trick. What you want is a universal quantum computer to do password cracking, for example, to solve neural networks and these kind of things. That is much more interesting. That you have from a universal quantum computer. And so, for example, IBM Q is one of those efforts for universal quantum computers. The reason why I mention IBM is not that I'm sponsored by them, but because you can go here and you can use it on the internet. I think they have a 5-qubit thing that you can just test for free once, and then you have to pay for it. And there are some 20 or almost 50 qubits that are available. So that is a really remarkable and new way of doing things. Not forcing everyone to buy the used fridge, but having the used fridge in one place. And basically the processor sits in that thing here, and the used fridge cooling down stuff. And you are able to program through some kind of web interface. That's a very interesting way of doing things. And the way you program it is, of course, not by C, C++, Python, or R, or whatever. You have a specific language to talk with your qubits. And so the reason why I was showing those 4 cards in the very beginning of the presentation is that 4 cards can be presented by 2 qubits. This is up, up, this is up, down, this is down, up, and this is down, down. And so I can present the 4 cards with just 2 qubits. And that is exactly what is being done here. So here we're working on the 5-qubit machine of IBM. We only need 2 qubits. And then we do some operations. So these blue boxes are operators. You see here we have some addition operator. The Hermitian turns the spin around, something else. And in the end, what is important is that you have the pink one, which is the readout. And then you have the state of the first qubit, up, down, and the second one, down, up. So it should be this card. That is more or less how it works. And by the way, that trick about the cards is pre-programmed. You can just go there and test it by yourself. And magically, the quantum computer will almost always find the right solution in a stack of 4 cards. If you have more cards, you need a slightly more complex algorithm, but with your 5 qubits, you can already do a lot more. So you see here you have 4 cards. With a third qubit, you have 8 cards. With the fourth one, you have 16 cards, you have 32 cards. So it becomes already interesting. And we are today really at the verge of doing interesting things with those machines. So to summarize, what we can do is, of course, optimizations. The D-wave type of thing is possible. And here is the algorithm. And we can, of course, searching in unstructured data. So we can find the right card without a trick, which is, of course, obviously good if you have a lot of data like Google, so you can find a lot faster your stuff. You can also crack passwords because however encryption key that we're using today, quantum computer has a way to somehow crack it a lot faster than classical computers. We can also solve these kind of large linear systems that are sparse. Sparse means there are a lot of zeros in it. Okay, that's not so important. What that does is solving multi-layer neural networks. And when you say multi-layer neural networks, you say more intelligent machines. And maybe at some point we can have a machine like was imagined by Mark Slane in Brussels in 1969, where he has a computer that is that box here that basically understands what's going on in the human world. And so this person basically asks a question and he writes it on a paper because keyboards weren't common good at those days. We were still using the punch cards, and the computer basically writes a solution. And the thing that he is asking is he has some kind of marital problems, and so he asks advice on how to interact with his wife. That type of things our computers can't answer now. Once we crack that problem with the quantum computers, we can imagine intelligent machines that can excel not only in a narrow part of intelligence like driving, but also in a general sense like operating like humans. What problems we can solve with quantum computers is not yet entirely clear. We know that we can do a lot, and P problems are the ones that can be solved in polynomial times. So in something like quadratic third power times, so not exponential. NP complete are the ones that are way too complex, traveling salesman problem. What we're hoping is that the quantum space is that dotted line here that is slightly bigger than the P problems, but honestly, at this point, we don't know. It really is early days in quantum computing. We are, however, very, very close to something that we call quantum supremacy. And that means that we are very close to solving a problem with quantum computers that practically we can never do on a classical machine. The expectation is 50 qubits are needed to get quantum supremacy. And frankly, we have that more or less. We have problems to keep it coherent, so to keep those quantum states nicely connected as a quantum state and not disturb them too much long enough. But once that engineering problem is solved, there is no other technical or theoretical obstacle to solve problems that otherwise we never practically could solve. And honestly, we really are close. For example, we recently had certain things in the news that Google was able to solve certain things that they thought they had quantum supremacy, but then the competing IBM said, well, actually you have a smarter algorithm here with a normal, let's say, a supercomputer can solve it in a few days. So you're not really in quantum supremacy here, although you are really very, very close. So definitely watch that space. A lot of things are happening. So that is the article that was published on the back of this claim of Google that they had quantum supremacy not so long ago, October 2019. And now 2 weeks ago, we had Goldman Sachs using a quantum computer to do something real. In the meanwhile, we had also Zoom, the company that we're using right now to talk to each other, to basically make an April's Fool's joke on the 1st of April of 2021 using quantum computer and basically have just a messy conference call where people got disconnected at random times. That's of course not a useful application. But we really are at the eve of a very exciting thing. Now, quantum computers, don't understand me wrong, they're not here to push AI and machine learning away. AI, machine learning, big data, Internet of Things, and the words that you had on the whiteboard, I really believe those things will be the takeoff of the next wave. Those things are ready, quantum computers not quite, but when they come, it will be massive. It will be disruptive. We will have new medications. We will solve cancer. Cancer is related to folding of proteins, way too complex to solve for classical computers. We also will have to review our encryptions, and we will have much more intelligent systems. Or we will hit a hurdle and we have to rewrite the laws of physics. Either way, I think we're in for some very interesting years to come. All right, that was what I had prepared for today. I think we just hit the magical border of 12:31. So I think we can stop here unless there are some burning questions.
No, thank you. Very interesting lecture.
Oh, lovely. Thank you
so much
for the feedback.
I'm not trained in life sciences or in physics or mathematics, but that was extremely interesting, at least for indications and fields I work for. So thanks a lot for this.
Yes, that's great. I think there is a lot of value in understanding the big picture. And mathematicians usually they dive too fast into too much complexity, and then it's pretty hard to understand anything. And honestly, quantum mechanics, you can't understand it anyhow. So if you understand the big concepts, you get some idea about what magic is possible, or about the machine learning things. So you see that you can, with very simple rules, fit certain outcomes with your neural network, or separate things in different groups. But honestly, those things are very vulnerable. Say a neural network can try to recognize traffic signs, for example, and it does that really pretty good. You give it 1 billion pictures and it finds always the answer on those 1 billion pictures. And then you have one traffic board in which you put a small sticker and it fails because it is overfitting. So there is a lot of danger in overusing those things, and we have to be careful with them. Okay, thank you so much for the feedback, Mikołaj. Anybody else?
Thank you very much as well from my side. A very valuable lesson for me as well.
Okay, thank
Good
you.
time spent today. Thank you.
All right, okay, lovely. Thank you all for your attention. I wish you a great afternoon for what is rest of your Sunday, and a lot of success with the end of the MBA and in all the things that you will do after the MBA, because that's where it really starts. Thank you all. Have a lovely day. Bye.
Thank you.
Thank you. Bye-bye.
Thank you. Goodbye.
Thank you very much.